All right, people. Well, welcome back. We're going to start here today on section 3.5, which is called rational functions. So what is a rational function? A rational function is one that is a ratio of polynomials. So what's the, sort of commoner term for ratio is a fraction. A fraction where the top and bottom, or the numerator and denominator, are polynomials. So I know we've been discussing polynomials before our extended break, but perhaps we'll need a refresher on what is a polynomial, right? It's a sum of whole number powers of x times scalar coefficients, or times real number coefficients. So polynomials, I think we discussed, have domain all real numbers. So rational functions, the only problematic x values for rational functions are x values that make the denominator q of x equal to 0. So our domain will be all x for which q of x is not equal to 0. So here they've given us a few here. The first one is f of x is 3x minus 1 over x plus 5. They say find the domain. Well, we'll need that x plus 5 is not equal to 0, right? Because the first commandment of mathematics is that we do not divide by 0. So if x plus 5 is not equal to 0, then x must be not equal to minus 5, right? If we'd like, we could write that domain in the interval notation as the interval from minus infinity to minus 5 union the interval from minus 5 to infinity. Obviously, neither one of those will include minus 5. All right, the next example they give us is g of x equals to x divided by x squared minus 3x minus 10. And again, we'll need that the denominator is not equal to 0. So we got x squared minus 3x minus 10 is not equal to 0. So let's see what we can do. Well, can we factor this side? I think we can. I think it factors as x minus 5 times x plus 2. So we need that x minus 5 is not equal to 0, and we also need that x plus 2 is not equal to 0, as either one of those being 0 would make the product 0. So x cannot be equal to 5, and x can also not be equal to minus 2. So we have now two x values that are inadmissible in this context. So if we wanted to write the domain for this one in interval notation, oh gosh, we only need 3 intervals to take the union of. We'll have the interval from minus infinity to minus 2, union with the interval from minus 2 to 5, union with the interval from 5 to infinity. That's very nice. Okay, now how about this last one? They give us 8x squared minus 1 divided by x squared plus 9. We need that x squared plus 9 would not equal to 0. But I'm pretty sure that x squared plus 9 never actually equals 0. Think about it. So if you take a real number and square it, then it becomes greater than or equal to 0, right? So x squared is always greater than or equal to 0. Then when we add 9 to that after the fact, the result that we get is always greater than or equal to 9. So in particular, it will never be equal to 0. So any real number x can go into this expression, and the denominator will not be 0. So the domain in this case is all real numbers, or rather the interval from minus infinity to infinity. Good. So that's the only thing going on with the domain of a rational function, is that you just need to make sure that the denominator is not equal to 0. Okay, and now they're going to give us a little bit of notation, because we're going to start talking about some asymptotes, and we need maybe some notation to discuss asymptotes. So this first bit of notation that has x with an arrow to a letter c that's going to stand for a number with a little plus sign above it, what this you can read as is x approaches c from the right. That's what this plus sign means, from the right. So similarly, this x approaches c from the left is denoted the same way, but with a little minus sign above the c to denote from the left. Okay. This bit of notation here, x with an arrow to infinity, means x approaches positive infinity. And similarly, the x with an arrow to negative infinity can be read as x approaches negative infinity. So let's take a look at this rational function. I think it's probably the most famous rational function, or maybe the most basic one. f of x equals to 1 over x. What happens as x goes to 0 from the right? Well, let's see. As x goes to 0 from the right, that means we'll start over here to the right of x equals 0. And imagine running along the x-axis going towards 0, and look at what the f of x values go to. It looks like as x values get closer and closer to 0 from the right, the f of x values go off to positive infinity here, right? They never seem to touch this line, the y-axis, and they get just infinitely bigger. So we can say as x goes to 0 from the right, f of x goes to positive infinity. Now let's take a look from the other side. As x goes to 0 now from the left. Well, as x goes to 0 from the left, we're moving closer and closer to 0, coming from the left side x values. Now let's look at the corresponding y values. They are getting smaller and smaller, going off to negative infinity, right? So here we can say as x goes to 0 from the left, f of x goes to minus infinity. Okay, how about as x goes to infinity? That would be like, or as maybe we could say x goes to positive infinity. Then that would be like looking at what happens as the x values move all the way off the picture here, right? It looks like the corresponding y values keep getting closer and closer to 0. So we can say as x goes to infinity, f of x goes to 0. Okay. And similarly, as x goes to negative infinity, so if we move off forever in the left direction, then the y values again get closer and closer to 0, but from the negative side. That's fine though. So we can say that as x goes to minus infinity, f of x goes to 0 as well. So in this picture here are really the two phenomena that we're going to try to observe and maybe see if we can't analyze more about in general rational functions. Namely, that we have a vertical asymptote here at x equals 0 and a horizontal asymptote here at y equals 0. So let's say a little bit more about vertical asymptotes. So a vertical asymptote of a graph is a vertical line where the function sort of approaches either infinity or negative infinity on either side of that line. So it can kind of like be opposite, or it can come to the same infinity on either side. That's fine. Both of these would be instances of there being a vertical asymptote here. But vertical asymptotes are going to occur at places where our rational function is undefined. So there'll be places outside the domain of the rational function. Now, that's a kind of a warning, though, that not all places outside the domain of our rational function are going to be the site of a vertical asymptote. But it's a starting point, at least. So here is the full way to find the vertical asymptotes of a rational function. The first thing you will do is reduce the function to lowest terms. So p of x and q of x could have some common factor. The first thing you want to do is divide out that common factor. And then you'll be left with a rational function where all you have to do is find what's not in the domain. And those x values will then be the site of your vertical asymptotes. So let's see it in action. In this example, we have the vertical asymptotes of 5 divided by x plus 3. Well, I don't think there's any factors common to 5 or x plus 3. So we don't need to do any dividing. So all we need to do is say, when is x plus 3 equal to 0? And when does that happen? That happens when x is equal to minus 3. So on this function here, we should get that x equals to minus 3 is a vertical asymptote. And I think you might recognize that this one is just a transformation of 1 over x. So we could take the graph of f of x equals to 1 over x, shift it to the left by 3, and then vertically scale it by 5. And we'd be getting this 5 over x plus 3 here. So that vertical asymptote of x equals 0 is shifted over to the left by 3, becomes x equals minus 3. Okay, for the next example, we'll find the vertical asymptotes of m of x, which equals to x plus 9 divided by x squared minus 81. Ah, well, maybe there's some work to do here. We'll first reduce the function to lowest terms, right? So it looks like x squared minus 81, that is a difference of squares. And if you remember from written homework number 1, the difference of squares will factor now as x plus 9 times x minus 9. But oh, x plus 9 is a factor that is common to both the numerator and denominator of this rational function. So let's divide it out, and we'll be left with 1 over x minus 9. And so I have this little squiggly equal sign here to remark that these two feel like they morally should be the same, although there's one place where they are not quite the same. And that place is at x equals to minus 9. There's something else a little bit more subtle going on there, but we'll talk about that maybe in class, or maybe we'll talk about that at a later date. So for now, just note that the only vertical asymptote that happens here happens when x minus 9 equals to 0, or namely when x equals to 9. So your quiz for this lecture is about a problem that's, I think, sort of similar to this, where you have to do a little bit of factoring and dividing out to determine what is the vertical asymptote of some given rational function. Okay, so let's move on. The next example is about finding the vertical asymptotes of x minus 7 divided by 2x squared plus 5x plus 2. Now, 2x squared plus 5x plus 2 factors, but we have to use what's called the good old AC method, which you also might remember from written homework 1. So we'd like two numbers whose product is a times c, namely 2 times 2. So we want two numbers whose product is 4, and whose sum is the middle guy 5. And I think 4 and 1 will get it, because 4 times 1 is 4, and 4 plus 1 is 5. So now we'll write 2x squared plus 5x plus 2 as 2x squared plus 4x plus 1x plus 2. Just breaking the 5x into the two pieces of 4x and 1x. And now we can factor by grouping. So in the first two terms, we can factor out 2x, and we're left with x plus 2. And in the next two terms, we can factor out 1, and we're left with x plus 2. And now, in this expression, we have 2x times x plus 2, plus 1 times x plus 2. So x plus 2 factors out. And we have then 2x plus 1 times x plus 2. So now we can factor the bottom completely, and we can write p of x equals to x minus 7 divided by the product 2x plus 1 times x plus 2. I don't see any common factors here, so there's no need to do any dividing out. So all we need to do now to determine where the vertical asymptotes occur is to set the two factors from the bottom equal to 0 and solve for x. So when 2x plus 1 equals to 0, we get x equals to minus a half. Just subtract 1 and divide by 2. And when x plus 2 equals to 0, we get x equals to minus 2. So there's two vertical asymptotes for this particular rational function. They occur at x equals to negative 1/2 and x equals to negative 2. So stay tuned for this second part of this lecture, where we will discuss not vertical asymptotes, but horizontal asymptotes. We'll see you then.